But both the places I can't run the PPT, no, ma'am. Anyway. Okay, ma'am. Yeah, okay, ma'am. Deep learning finds application everywhere in like in media, entertainment, security, defense, also in autonomous machines like in the Tesla car and everything. You see, deep learning plays a very important role. Not only in that, in media or entertainment, like in case of real-time translation, video search, video captioning, they are not we can able to find this deep learning applications. This is the elements of neural network where it has input neurons and output neurons will be having. Also, we'll be having hidden neurons. So the hidden neurons, the hidden layers, anchored like sigma is nothing but activation function, omega 1x plus b1, where omega 1 is the weights of the particular neuron and b1 is the bias. Similarly, the output layer y corresponds to sigma of omega 2h plus b2, where this omega 1 and omega 2 are the weights and b1 and b2 are the base. This is the basic elemental neural network. So in this case, if you take, you have like a 4 plus 2 neurons are there. So we are not counting inputs here. Totally we have like a 4 plus 2, 6 neurons here. And weight, if you want to calculate, 3 into 4, that is 3 input neurons we have, and we have like hidden layers, 4 neurons. So we have to multiply these two and add these two multiplication, that is 4 into 2, 3 into 4 plus 4 into 2. Like we have to multiply and add all this to get the total weight as 20 weights. And totally if you see, number of biases here is going to be, for here 4 and here 2, so we will be having 6 biases. So for this simple hidden neural network ANN, we have totally 26 learnable parameters. So like that, if you take for this simple layer itself, if you have like 26 learnable parameters, if you are dealing with the deep learning, definitely you will be having more numbers of learnable parameters. So this is the basic function, how the activation functions work with the input. For example, here we have taken two inputs, x1 and x2, and x0 is the bias function, where x0 carries weight w0 and x1 carries the weight w1 and x2 input carries w2 weight. So the function f of x, we can take any of the activation function, like we have like so many activation functions. Normally we take this linear, sigmoid, tan x, ReLU, softmax, like we have like so many activation functions we have, we can take it. And if you take the deep neural network, for example, we have taken here, this is the matrix for this deep neural network, where we can able to give as the input to this deep neural network. For example, here we have taken the classes 0, 1.4, 2.7, 1.9. These fields we are giving as an input to this deep neural network. So once we give the input, ma'am, is it audible, ma'am? Hello?
Yes, ma'am, perfectly audible.
When we give the inputs to this artificial neural network, deep learning network, the input will be given here and these weights will be adjusted to give the output. For example, if you are taking the first fields as 1.4, 2.7, 1.9 as an input here, if you give, and then we can able to train these weights to give the output. For example, here the output is coming as 0.7. So it means it is having, one second, it means it is having an error of 0.7 here. So we have to make this error as equal to 0. It means that we have to adjust these weights. In between we have some hidden layers. In these hidden layers we have some weights. These weights we have to adjust so that we have to make this error value is equal to 0. So for that we have to repeat this step, maybe like sometimes 1,000 times, sometimes we have to make it for million times, like randomly we have to adjust this weights to get this error is equal to 0. That is what our aim is that in deep learning. So one second. For example, in case of your ImageNet, we have like so many numbers of images. For example, here total number of images are here is like 14 million images we have. So we can use these types of data sets like ImageNet for our applications in deep learning. Also we can use CFAR 10 data sets for our deep learning application. Normally if you're taking and doing work with the CNN or deep learning network, we use these data sets freely available ImageNet, or we can go for CFAR 10 data sets where we can have like totally we have here 10 different types of data sets, like for example airplane, automobile, bird, cat, deer. So 10 data sets we have. Totally we have here 15 training images and 10,000 testing images. 10 categories we have in this. So normally if you do the image processing with the normal machine learning network, what happens is that you'll be getting accuracy of less than maybe like 94-95% you'll be getting. When you go for deep learning, definitely you can improve the accuracy of your output. And this is the example for a deep learning convolutional network where we have the input image will be convolved and a max pool, and so once again dropped out, convolved, max pool, like we will be having, but the input image will be given to n numbers of convolutional layers followed by max pooling layers followed by dropped out. So like here the convolution layer filter works on every part of the image here. It will work on every part of the image, therefore it search for same type of features everywhere. Here in this image you see you'll be having like a boat images are there in the lake, right? So the similar type of boat image wherever is available in the particular image, it will be keep on searching for the image in this particular image. So the convolution layer, here this is what is called as convolution layer. It will be like a box. This box will be moved from this frame to second frame, like third frame, fourth, like it will be moving till it reaches the end of the pixel. So this entire image will be converted into pixel, and then it will multiply with this convolution filter. So like that the convolution output we will be getting. So here this is the input matrix, this is the convolution filter. So we have to move on this convolution filter over the entire image. Here this matrix we have to multiply with this particular input matrix. So that is what they did here. So first the input matrix will multiply with this convolution filter, and what is the result we are getting, it will be placed here for. Similarly this filter will be moving second, third, like it will keep on moving to the entire image, and we will be getting an output in this particular convolution filters output as some value. So when the convolution filters are scanned over the image, they capture the features. For example, here we have a filter over here. The filter will be moved over the entire image. So you'll be getting, when this filter is moved on through the entire image, you'll be getting some like line-like images we are having, because we used the edge detection filter here with this entire image. So we got a convolved image like this. Yeah. So in deep convolution neural networks, if for example we have taken a boat image here, so we have to multiply this with this input image. So when you multiply, right, you'll be having a big matrix, right? So we have to step down the image size, right? For that we have to go for what is called as max pooling, where we will be converting this entire 4 by 2 by 2 matrix into one signal element. Like what is the maximum value over here, it will be converted. And what is the maximum value here? It will be converted to